Welcome back. So we've finished chapter 2 at this moment, and now today we're going to start chapter 3, evaluating properties. When you describe something, we have to use properties. So for example, when you describe an engine, you have to use mass, you have to use length, you have to use volume. Those are all properties. Pressure and temperature are also properties. You have to use those properties to describe the state. Okay, so in this chapter, we just focus on properties and how you look for them and how you use them. Okay, the first one is introduction. Okay, phase. What is a phase? How many phases do we have? Usually we have four, right? What are they? Gas, liquid, solid, and the last one, plasma. All right, so usually we have four phases. And then what's the definition of a phase? Phase is a quantity of matter that is homogeneous throughout in both chemical composition and physical structure. That's the definition of a phase. And usually we deal with gas, liquid, solid, and the last one, plasma. Usually we have four phases. And in this class, usually we deal with gas and liquid. In this class, we deal with gas and liquid. Okay, so that's the first one, phase. And next one, pure substance. What is a pure substance? A pure substance is one that is uniform and invariable in chemical composition, as long as they have the same molecule, and then it's called a pure substance. Okay, so for example, what if we have oxygen? Is it a pure substance? Yes, because all the molecules are the same. It's O2. So yes. What about nitrogen? Nitrogen. Yes, again, because all the molecules are the same. It's N2. And then what about air? Is air a pure substance? The answer is obviously no, because air is a mixture of oxygen, nitrogen. They have different molecules. Okay, and one more. Water plus ice. Water and ice both together is the pure substance or not? Let's go back to the definition. The requirement is uniform and invariable in chemical composition, which means they have to have the same molecule. Do water and ice have the same molecule? Yes, they do, and that is H2O. So, yes, because they're just H2O, they have the same chemical formula, H2O. The only difference between them is they have different physical structure. One of them is liquid, the other one is solid. But it doesn't matter because the only requirement for you to call something pure substance is they have to be uniform and invariable in chemical composition. Okay, so that's pure substance. All right, and then next one, we move on to the three properties that are really, really important for this class. What are they? First one, pressure. Second one, new, specific volume. And then the last one, T, temperature. Okay, this one again is new, which we introduced in the first week of class. New. Okay, just in case you forgot, what is new? Specific volume has a definition, that is volume over mass. Okay, we learned this in first week. Okay, so here under P nu T, pressure, specific volume, and temperature, we introduce two diagrams. Two diagrams. The first diagram is P, pressure, versus nu diagram. The second diagram is T, temperature, versus nu diagram. Okay, and each of them has a vapor dome. This is called a vapor dome. Okay, and be careful here because the dome is not exactly symmetric. The left half of the dome is more steep, okay, while the right half is less steep. Okay, it's not perfectly symmetric. All right, so you have vapor dome. Those two domes have a name. They're called vapor domes. Okay, how do we use those two diagrams? Those two diagrams are actually very, very useful. So for example, if you're an engineer, you usually deal with what? Pipes. And what's inside those pipes? We don't know. It can be, for example, steam, which is gas. It can be liquid water. It can be a mixture of liquid water and vapor. And is there any way for us to know exactly the phase inside the pipe? It's really, really difficult. Why? Because we cannot see. We cannot see what's inside the pipe. So how do we determine the phase of the substance inside the pipe when you work with those things as an engineer? You cannot just say, okay, I'm gonna cut the pipe and take a look and put it back, right? It doesn't work that way. So how do we determine the phase of the substances? What we do is we can measure, for example, pressure and specific volume at a location inside the pipe. And then, because we measure the pressure and nu, specific volume, on this P versus nu diagram, you will have the y coordinate and also the x coordinate. That will give you a point on this diagram. And based on the location of the point, we can easily tell the phase of the substance. So for example, after you measure the pressure and a specific volume, which are the x coordinate and y coordinate on this diagram, you're going to have a point. If the point falls onto the diagram somewhere here, to the right side of the vapor dome, to the right side of the vapor dome. As long as the point falls onto the right side of the vapor dome, then your substance must be vapor. Must be vapor. And then if the point falls onto the left side of the vapor dome, for example here, left side of the vapor dome, and then your substance must be liquid. Must be liquid. And then next one is, what if the point falls within the dome? If the point falls anywhere within the dome, such as here, it must be a mixture of liquid and vapor. Liquid and vapor. If the point falls anywhere within the vapor dome, it must be a mixture of liquid and vapor. Okay, and then the top point has a name, it's called critical point. Critical point. All right, and then the next one is, what if the point falls right on the vapor dome? What if the point falls right on the vapor dome? Okay, so now let's change the color to, let's say, red. All right, so two cases. What if the point falls right on the left half of the vapor dome? What's going to happen? If the point falls right on the left half of the vapor dome, it has a name. It's called saturated liquid. Saturated liquid. What if the point falls right on the right half of the vapor dome? If the point falls right on the right half of the vapor dome, right on the dome, indicated in blue, it also has a name. This time it's called saturated vapor. Saturated vapor. Okay, so by measuring P, pressure, the y coordinate, and a nu, specific volume, the x coordinate, you can locate a point. And then based on the location of the point, you can easily find out the phase of your substance without visually seeing it. Okay? To the left of the vapor dome must be liquid. To the right side of the vapor dome, it must be vapor. Within the vapor dome, it must be a mixture of liquid and vapor. Right on the left half of the vapor dome, indicated in red, it must be saturated liquid. Right on the right half of the vapor dome, indicated in blue, it must be saturated vapor. Okay, so that's P versus nu diagram. Okay, very similar to P versus nu diagram, we have T, temperature versus nu, specific volume diagram, because sometimes it's easy to measure pressure, while other times it might be easier to measure temperature, so you do have a choice. And then we have the second diagram, which is a T versus nu diagram. Okay, for T versus nu diagram, you also have this dome. It's also called vapor dome. And then you can measure temperature, which is the y coordinate, and then measure nu, which is the x coordinate. Based on the x and the y coordinates, you can have a point. And then again, based on the location of the point on this diagram, you can tell the phase of the substance. So you don't have to take a look, you just have to measure temperature and the nu, and then you will know what's the phase of your substance inside the pipe without looking. Okay, so again, it's going to be the same. To the left of the vapor dome, your substance must be liquid. Must be liquid. Okay, must be liquid. Okay, to the right of the vapor dome, again, must be vapor, same as before. And then within the dome, it's still liquid plus vapor. Okay, same as before. And then the top point, it still has the name critical point. All right. And then the left half of the vapor dome, still exactly the same as before. If it falls right on the left half of the vapor dome, then the substance must be at saturated liquid. And then same as before. If it falls right on the right half of the vapor dome, indicated in blue, then the substance inside your pipe must be saturated vapor. Okay, so those are the two diagrams. we introduced today. The main purpose of the two diagrams is to help you decide what's the phase of the substance by measuring the properties so you don't have to visually look at it, which may not be possible usually in work. Okay, so a few things we need to point out. Okay, first one, saturation state. Saturation state. What is a saturation state? So today we have two saturation states. First one is called saturated liquid. The second one is called saturated vapor. What do they mean? What do they mean? So to understand them, we have to understand the definition of a saturation state. A saturation state is a state at which a phase change begins or ends. Okay, so now let's think about this scenario. You have a pot of water, you put it on the top of your oven, you turn the gas on, so you add heat to the water. What's gonna happen is the water is gonna become warm, warmer, warmer, and hot, and then at a moment it's gonna start to vaporize. The moment it starts to vaporize. In other words, changing phase. The beginning of a phase change from liquid to vapor is called a saturation state. And at that moment, when liquid starts to vaporize, you call it saturated liquid. That's the definition of saturated liquid. That's when the phase change from liquid to vapor starts. Okay, and now you continue heating up the water, you continue heating up the water. So you're gonna have less and less liquid, more and more vapor. And then at a certain point, what's gonna happen is all the liquid will disappear and you have only vapor left. So this is an end of a phase change from liquid to vapor. This is the end of a phase change, which is also called a saturation state. And this at this moment is called saturated vapor. Saturated vapor. Okay, so that's the definition of a saturation state, which helps us understand saturated liquid and a saturated vapor. Okay, in other words, saturated liquid is the beginning of vaporization from liquid to vapor, while saturated vapor is the end of vaporization. You don't have any liquid left anymore. You only have vapor. It's the end of the vaporization. Okay, and then next one, the two domes on the diagrams have a name. It's called vapor dome. Okay, the name of the two domes is called vapor dome. And then next one, which we already explained, saturated liquid and saturated vapor. This is what? The beginning of vaporization. And this is the end of vaporization. No liquid left anymore. Okay, and then the next one is the critical point. All the properties measured at this point have a subscript P critical, T critical, nu critical. And what is T critical? T critical is the highest temperature at which liquid and vapor can coexist. Okay, and then the next one, phase diagram. Phase diagrams. Okay, the two diagrams which we introduced today are still P versus nu diagram, the first one, and the second one is T versus nu diagram. Okay, and remember the first thing you need to do is always to draw the vapor dome. Steep, and right half is less steep. Okay, steep, and right half is not as steep. All right, two vapor domes. Remember, they're not exactly symmetric. Okay, on a P versus nu diagram, we have something called a constant temperature line. How do you sketch a constant temperature line? Here, you have a curve. Okay, remember this is a curve. It's not a straight line, it's a curve going down. And then you have a flat line within the dome. It's flat. And then you curve down again. You curve down again. This is called a constant temperature line, constant temperature line, meaning every point on this line has the same temperature. Every point on this line has the same temperature, and you can have many, many such temperature lines. Okay, go down, straight, and then curve down. Okay, so for example, this one, the top one can represent the temperature T1, while the bottom one can represent a different temperature T2. Okay, so every point on the top line must have the same temperature, which is T1, and every point on the bottom line must have the same temperature, which is T2. Okay, and the rule is T1 is greater than T2. The higher this constant temperature on line is, the higher the temperature it represents. Okay, and now let's move on to T versus nu diagram. On a T versus nu diagram, we have something very similar. It's called a constant pressure line. How do you sketch this line? Very similar. Curve up this time. Okay, it's a curve up, and then straight line, and then continue to curve up. This is a constant pressure line, meaning every point on this line has the same temperature. You can have multiple such lines. Let's say we have two. The top one we call P1, the bottom one we call P2. So any point on the top line has the same temperature, same pressure, which is P1. And every point on the bottom line has the same temperature, which is P2. And the rule is the higher this line is, the higher the pressure it represents. Because the line P1 is higher, so the pressure P1 must also be higher. Okay, so that's the rule. The higher this line is, the higher the pressure it represents. Okay, so those two diagrams are very, very useful because they're going to help us understand the process. Okay, so we're going to do one example to show you how using those two diagrams can help us understand the process. Okay, so next one, phase change. Okay, so now let's do this. You have an engine, okay, or you can think of this as a pot of water inside a piston cylinder assembly, okay? And then here you have some liquid. You can think of it as water. Okay, and now you start to give it heat, provide heat. What's going to happen is some of the liquid will become vapor and the volume will become bigger. So it's going to push up the piston. You have some vapor and you're going to have some liquid and the volume will become bigger. And what if you continue heating it up? What if you continue heating it up? What's going to happen? You will have more vapor and less liquid. And at some point, you'll have vapor only. And then the volume will be even bigger. Vapor only. Okay, so this is a process how you boil up some water. You provide heat. Water is going to start boiling, which means it's going to give you more vapor. And what if you don't stop? What if you continue heating it up? You're going to end up with only vapor and no liquid. This is a constant pressure process. It's a constant pressure process because the piston moves freely. Okay? If the piston cannot move, then the pressure inside will go up. However, if the piston can move freely, then the pressure will remain constant. So later on, when you see the phrase piston can move freely in a problem, then you should understand this tells you the pressure is constant. Okay? All right, so now what we're going to do is we're going to sketch this phase change diagram on the two diagrams. We're going to sketch the phase change process on the two diagrams. First one is P versus nu. Second one is T versus nu diagram. Okay? Whenever you use the two diagrams, the first thing you do is always the same, which is to sketch the vapor dome. Okay, remember, steep and then less steep. Okay, same thing, steep and then less steep. Okay, so first thing is always the same. Sketch the diagram and sketch the two vapor domes. Okay, so let's start from number one. We start from point one. Okay, we're gonna start from point one. We're gonna start from point one. Okay, point one will just be tap water, tap water. And then you start from point one, which is tap water, which is cold, right? Tap water is just cold. And then you give it heat. You turn the oven on, you give it heat. What's gonna happen? It's gonna gain heat and it's gonna become warmer and warmer and warmer until the moment when it starts to vaporize. Okay? Number one is tap water, and then you keep giving it heat. At some moment, it's gonna be, after some time, it's gonna reach a point when it starts to vaporize. Okay, so this one we call 1 to F. Number one is tap water. Point F is the moment when it starts to vaporize. Do you remember the name we call F? It's the beginning of a phase change from liquid to vapor. It's called saturated liquid. Okay, point F has a name which we introduced already. It's saturated liquid, meaning it's the moment when liquid starts to vaporize. Okay, what do we call tap water number one? It's called subcooled. Subcooled liquid. Okay, subcooled liquid. So that's 1 to F, that's the first step. All right, so how do we sketch 1 to F on this diagram, on those two diagrams? We're going to sketch this process on those two diagrams. Okay, let's start from P versus nu diagram. P versus nu diagram. A very important thing we need to remember is this is a constant pressure process. Constant pressure process. And then what is my y coordinate on the P versus nu diagram? It is pressure, meaning the y coordinate for this process doesn't change, right? Because pressure has to remain constant. So the y coordinate doesn't change. If y coordinate doesn't change, it must be a straight line for this process because the y coordinate doesn't change. If the y coordinate doesn't change, it must be on a horizontal line. Okay, it must be on a horizontal line. Okay, so now let's look at number one. Where's number one? Where do you put number one on this dash line? Number one is tap water. It must be liquid. Do you remember the location for liquid on the diagram? Let's go back. If it is liquid on a P versus nu diagram, it must be to the left of the vapor dome. Okay, so to the left of the vapor dome for liquid, number one must be somewhere here. That's where tap water is. We call subcooled. And next one, 1 to F. What is F? Saturated liquid. Where is saturated liquid? Do you remember? If you don't, let's go back to the diagram. Here, P versus nu diagram. Where is saturated liquid? It's in red. So the right half of the vapor dome. So it must be right on the dome. This is where point F is. Point F. Okay, 1 to F to the right. And F must be right on the left half of the vapor dome because it's saturated liquid. That's 1 to F. Okay, next one. What if you continue heating things up? What if you continue heating things up? You start from F and then you continue. You continue giving water heat. What's going to happen? Okay, F is the moment when it starts to vaporize. And now you don't stop. You continue providing heat to the liquid. What's going to happen? You're going to start to have vapor, more and more vapor over time. And then after some time, what you're going to have is what? Vapor only. Vapor only. So we start from saturated liquid. And then you continue giving it heat, meaning you're going to have more and more vapor. After a while, you won't have any liquid left. You only have vapor. So that's the end of a phase change from liquid to vapor. It has a name, do you remember? It's called saturated vapor, meaning you have vapor only left. There's no liquid. Okay, there's no liquid. It's called saturated vapor, the end of a phase change from liquid to vapor. And we have a letter for saturated vapor too. We use letter G. Okay, we call it G point for saturated vapor. So now can you locate point G? Can you locate point G? Saturated vapor. If you forgot, we can go back to this diagram. Okay, let's take a look at this P versus nu diagram. Where is saturated vapor? on the right half of the vapor dome indicated in blue. So point G must be on the right half of the dome. Okay, so point G must be on the dome, and like I said, must be along this dashed line because it is a constant pressure line. So G point must be right on the right half of the dome and also on this dashed line. So F to G must be a straight line. Okay, so F to G. And then next one, what if you start from G and you don't stop? You start from saturated vapor. And let's say you don't stop. You continue giving this vapor heat. You continue providing heat to the vapor. What is gonna happen? The vapor will still be vapor, right? But we have a name for it. It's called superheated. It's called superheated vapor. And for superheated vapor, we have a letter. We use letter S. We use letter S for superheated vapor. Okay, so where's superheated vapor on this P versus nu diagram? If you continue providing energy, providing heat to G point, and it's going to become vapor. So what's vapor? Where's vapor on this diagram? If you forgot, let's go back to the P versus nu diagram. Where is vapor on this diagram? To the right side of the vapor dome. So point S must be to the right side of the vapor dome. Must be somewhere here. Okay. G to S. Okay. S is saturated vapor. Remember, 1 to S here must be a horizontal line. This must be a horizontal line. Why? Because we said it's a constant pressure process. And on a P versus nu diagram, pressure P is the y coordinate, meaning the y coordinate doesn't change. If y coordinate doesn't change, it must be a horizontal line. Okay, so that's how we sketch everything on a P versus nu diagram. Okay, all right, so next one, what we're going to do is to repeat, but this time we're going to sketch everything on T versus nu diagram. Okay, again, it is a constant pressure process. However, this time my y coordinate is temperature. I don't know how temperature will change. So I need a constant pressure line. Where is constant pressure line? On a T versus nu diagram. Take a look at the right. Do we have a constant pressure line? How do we sketch a constant pressure line? Curve up, straight, and curve up. So now what we need is a constant pressure line here. Curve up, horizontal line, and curve up. This is a constant pressure line, meaning every point on this line must have the same pressure. Okay, since I have a constant pressure process, meaning the pressure for the whole process will remain constant, that means when I sketch this process, everything will be on this constant pressure line. Okay, everything will be along this constant pressure line. Okay, let's start from point 1, which is my tap water. Where's tap water? Tap water, point 1, must be on this P line. And also, what's the phase? Liquid, meaning to the left of the vapor dome. To the left of the vapor dome. Okay, if you forgot, let's go back to the diagram. Where's liquid on the T versus nu diagram? To the left of the vapor dome. Okay, and then 1 to F. Where's point F? Point F is saturated liquid. Where is saturated liquid? Right on the left half of the dome. So this is where point F is. 1 to F. Okay, and then F to G. Where is G point? the saturated vapor. Where is saturated vapor? Saturated vapor is right on the right half of the dome, just like before. This is where saturated vapor is, and it also has to be along this constant pressure line. Okay, F to G. And then last one, G to S. Where is vapor on a T versus nu diagram? Where is vapor? If you don't remember, let's go back. Take a look at this T versus nu diagram. Where is vapor? Here, to the right of the vapor dome. So point S must be to the right of the vapor dome, and also it has to be along this constant pressure line because it is a constant pressure process. So this is how you sketch 1 to F to G to S on a T versus nu diagram. Okay? Alright, so now you can see it's much better because you can visualize the whole process on the two diagrams. That's why we prefer to use those two diagrams. They're going to help us think. Okay? Alright, and then one more thing. What if the point is between F and G? If you take a look, what's between F and G? If the point is between F and G, it's within the vapor dome. If the point is within the vapor dome, what is the phase of the substance? If you forgot, let's go back to the diagrams. If a point is located within the vapor dome, it's a mixture of liquid and vapor. Okay? It's a mixture of saturated liquid, point F, and saturated vapor, point G. Okay, if we have a mixture, usually what do we need? We need to know how much each component takes up. So for example, in air, we know it's a mixture of oxygen and nitrogen. We know the percentage. Oxygen takes up 20%, while nitrogen takes up 80%. So now we have a mixture of saturated liquid and saturated vapor. I also want to know the percentage. How much does the saturated liquid take up, and how much does the saturated vapor take up? So that's why we introduce a parameter is called quality. Quality, and we use letter X for quality. The definition of quality is mass of the vapor divided by the total mass of the mixture. Or we can write it to mass of the vapor divided by total mass. What is total mass? Total mass is the mass of vapor plus mass of the liquid. This is the definition of quality. So it tells you the percentage that the vapor takes up in terms of mass. So for example, if I tell you the quality of this mixture is 20%, what does that mean? That means 20% of the total mass comes from vapor and 80% of the total mass comes from liquid. Okay? Quality X tells you the percentage of vapor in the mixture in terms of mass. Okay, all right. And next one, also a new concept, is called saturated temperature. Saturated temperature. What is saturated temperature? What's the definition of a saturated temperature? The temperature when the substance is at a saturated state. Temperature at which the substance is at a saturated state. For example, F or G. So the temperature of the substance at either point F or point G has a name. It's called saturated temperature. Okay, what is saturated pressure? It has the same definition. Pressure at which the substance is at a saturated state, such as F point or G point. Okay, they are saturated temperature and a saturated pressure. Okay, and then the last one, before we move on to an example, is how do we find those properties? We've been talking about the three properties, pressure P, specific volume nu, and a temperature T. How do we find those properties? We have the tables, and the tables that we usually use are A4, A5, A2, and A3. If you deal with water vapor, okay, in other words, between G and S, between saturated vapor and superheated vapor. As long as deal anything that is vapor, we go to table A4 in your textbook. And then if you deal with liquid, 1 to F, subcooled liquid to saturated liquid. Okay, if you deal with liquid water, that's usually table A5. And then if you deal with liquid and vapor, and the substance is water again, in other words, between F and G, between saturated liquid and saturated vapor, then usually we go to table A2 and A3. Okay, how do we use those tables? We will introduce one example to you to show you how we can use these tables to help you solve the problems.